In this video, we'll be looking at section 1.1.2. We'll be defining a general vector space. All right, so the goal is pretty simple. It's to define the concept of vector space. We'll also see a few examples. In the last video, in examples 1.1.1, 1.1.2, and 1.1.3, we saw that in three completely separate problems, the general solution was given as all linear combination on certain solution. And these solution sets corresponded to a span. In this chapter, we'll define an abstract structure that enable us to define spans and linear combination in various contexts. So we want A1V1 plus A2V2 plus ANVN, where these AIs are real numbers and the VIs are element of some arbitrary set. So V could be a set of functions, it could be a set of matrices, anything. For that, we must have a scalar multiplication so that we can make sense of each of these individual pieces, which multiplies the elements of V by real numbers. And we also need an addition, which adds two elements of V. So we need to make sense of this. These two operations need to respect certain axioms, which were true in vector geometry. So we're just generalizing vector geometries to other contexts, and we want to have the same flexibility. And those axioms will help us to prove important results later on. All right, so we're ready to define real vector spaces. Definition 1.1.1, I'm going to start with V. It's going to be a non-empty set, and I have two operations on V. I have an addition, which means that for any two elements of V, I have V plus W is defined. Scalar multiplication, for V and V and K and R, we have some information as to what KV is. All right, so we'll call V with these two operations a real vector space if the following axioms hold. So I need these 10 axioms to be true for V to be considered a real vector space. And by the way, here real refers to the fact that our scalars are real numbers. First, we need V to be closed under addition. That means for any two elements of V, their sum must also be an element of V. I want the addition to be commutative. That means if I look at V plus W, it should give us the same thing as W plus V. We need the addition to be associative. That means for any three elements, whether I add V plus W first, then add U, it's going to get the same thing as if I add U and V first, then add W. All right, so these two are elements of V and they should be the same one. Existence of the zero element. In vector geometry, we have the zero vector, and that proved helpful. We want the same thing in general vector spaces. So we need a special element, the zero, which we'll denote this way in V, so that for any element V in V, both V plus 0 and 0 plus V should give us V back. We need inverses, which means that for any V, I need an element which we'll denote by minus V. And if I add that element for V on either side, I will get the 0 element. All right, so these 5 axioms are called the they're called the additive. So the addition axioms. And now the next 5 axioms from 6 to 10 are going to be the multiplicative one. All right, so now we'll involve the scalar multiplication. Axiom 6, close under scalar multiplication. That KV needs to be an element of V, whatever K is. I need to be able to distribute scalar on the addition in V. That means if I start with something that looks like that, K times V plus W, I'm going to be able to distribute it and get KV plus KW. I need to be able to distribute scalar multiplication on the addition in R, so this time it's the real numbers that I'm adding, and V is there by itself, but again, I'm going to be able to distribute it, and I'll get KV plus MV. The multiplications must be associative, so here I have two different types of multiplication. I have multiplication of real numbers and then scalar multiplication on V, but I could see it in a different order. I could do one scalar multiplication by multiplying V by M, and then afterwards multiply whatever I get by K. Those